This presentation focuses on introducing a non-cooperative game framework for developing artificial intelligence to objectively evaluate the strengths and weaknesses of constitutive models. The idea comes from adversarial deep learning on models, which can efficiently search the model's failure cases and then increase the robustness of the model. One famous example is the generative adversarial networks, in which two models, generator and discriminator, compete against each other, so that increasingly the generator's image generation capacity is improved. For constitutive modeling of a material, one important process is the data collection, and it involves a lot of decision makings on what experiments to perform, so that the gathered training or calibration data can lead to a model with the widest applicability. Here we introduce a protagonist agent which can choose from a lot of experimental choices. For example, for soil materials, uniaxial test, triaxial test, and shear test. The goal is to gather the calibration data for models, and the model's accuracy on this data are maximized. Meanwhile, for gathering the testing data to evaluate the model's forward prediction accuracy on unseen scenarios, we introduce the adversary agent, which can also choose from a lot of experimental choices, but now the goal is the opposite. So the goal is to find the testing data on which the model's prediction accuracy is the worst. So the model's accuracy on this testing data are minimized. This creates a competitive scenario which the model's strengths and weaknesses are both estimated simultaneously. The decision makings involved in design of experiments can be recast as decision trees that are easy for human researchers or experimentalists to work on. Here is a simple decision tree example. First, you can decide the initial pressure of the soil sample. Then you decide which type of experiments to do. Thirdly, you can choose the final strain level. Each walk in the tree represents one chosen experiment. For example, this green walk represents 300 kPa, do the triaxial extension test, and then load until 1% strain. Note that the data collected have significant impact on the final chosen model. If this is the training data, then you might just satisfied with a linear model or a plasticity model with a slight strain hardening. But if this data on 400 kPa triaxial compression and load until 3% strain level is used as the testing data, then the previous model would not work because it lacks the pressure dependency, directional dependency, and it lacks the strain softening. Normally, the decision trees in this process will be so large that it's impractical for human researchers to work on. For example, this tree has more choices for initial pressure, initial sample void ratio, the type of experiments, and also introduce the loading, unloading, reloading to account for path dependency. So now this big tree needs the AI to take over this huge burden of finding the optimal training data that can lead to a best model, and also spotting the model's weaknesses inside all of these choices. For computer agents or AI, we need to formulate this non-cooperative game environment in which the protagonist can perform experiments on the material to gather the calibration data for the constitutive model. Meanwhile, the adversary can choose experiments on the material for testing data for the already calibrated constitutive model to make forward predictions on this testing data. The goal for the adversary is to make the model look as bad as possible so it works competitively with the experimentalist. This is a very challenging game that the Nash equilibrium are hard to find because it's non-cooperative, is also not symmetric because the payoff of a particular strategy depends on whether the protagonist or adversary is playing. Is also non-zero sum because the rewards for the agents do not add up to zero. It's sequential because the adversary is aware of the protagonist's strategy in order to attack accordingly. It's also imperfect information because the protagonist does not know how the adversary will attack. The optimal policy of protagonist agent in finding the calibration data and also for adversary agent for spotting models' weaknesses are automatically figured out by multi-agent deep reinforcement learning. This is based on AlphaZero developed by DeepMind to play on a lot of challenging games like Go, chess, and a lot of video games. So this can create AI to play and learn from trial and error on generating tests automatically until the Nash equilibrium of the game is approximated. The first example is on the traditional Zucker-Prager plasticity model. The material is discrete element method RVEs. The game choices are included in this big decision tree I introduced earlier, which has the loading, unloading, reloading path choices. At the beginning of the reinforcement learning, both agents do not know how to play the game properly, so they are just doing trial and errors a lot and getting experiences. But after a number of training iterations of the reinforcement learning, the protagonist now knows that the DP model is best at capturing the monotonic loading behavior, while the adversary is only focusing on this very complicated loading, unloading, reloading behavior. This is a good exercise to check because it's very well known that DP model have these strengths and weaknesses. It's important to know that this, starting from the randomly playing to the final conclusion that is consistent with human knowledge, that this process does not have any human intervention. It's all automatically figured out by the computer. The second example is on machine learning traction separation models. The material now is DEM for interface. The decision trees now includes shear tests with different normal openings and shear displacements. And you can also design different loading, unloading, reloading paths. The material now is recurrent neural nets, which can adapt to different calibration datasets. This is in contrast to the previous Zucker-Prager model, which is fixed. Because of the adaptivity of the machine learning models, all calibrations are perfect, The important thing is how an adversary agent attacks. At the beginning, because the calibration data are not representative enough, so it can spot these weaknesses for forward predictions. But by keep searching for weaknesses, it can drive the protagonist to yield the better calibration data and then train better model. So in the end, the worst case scenario from the adversary is like this. This is an example that this competitive mechanism can increase the robustness of machine learning models. For conclusion, this framework emulates idealized scientific collaborations and computations for better understanding of the application range of constitutive models, especially finding out the weaknesses in an unbiased manner. The computer can take over the large amount of trial and error burdens in exploring manually the experimental decision trees. This framework can be applied to both human-crafted constitutive models for spotting strengths and weaknesses, and also increase the robustness of machine learning models given better calibration and testing data. For more details, please see the published work in CMAME.